In this particular lecture, we'll discuss the frequency shifting property, and we'll also discuss some problems related to frequency shifting property, or how we can apply frequency shifting property in problem solving. Okay, all these questions are very important. You can see a slight difference between the questions, but you will get different answers. Okay. And now we'll start with the first problem. First, the definition of frequency shifting. So here you can see that a signal x of t, and assume that it's a continuous time Fourier transform, that is CTFT of this particular signal is represented by x of j omega. Then if there is a signal of the form e raised to j omega 0 t into x of t, or you can say that if you multiply a signal x of t with e raised to j omega 0 t in the time domain, it will be equal to x of j omega minus omega 0 in frequency domain. Or in other words, we can say that this is equivalent to the frequency shifting in the frequency domain, because omega minus omega 0. Previously, we also explained another property, that is a time shifting, then it becomes x of t minus t0. Now the shift is performed in the frequency domain, and that's why it's known as a frequency shifting property. So multiplication of x of t by a complex exponential signal e raised to j omega 0 t is also called a complex modulation. And so we'll also see this particular property or particular portion when you do the problems. Okay, so this is equivalent to actually the modulation operation. And when you perform this complex modulation time domain corresponding to a shift of x of j omega in the frequency domain. Okay, the same thing we explained in words. So this is also very important property, because we need this particular property to solve many problems. So we can consider this property as a frequency shifting property, because the frequency domain we are shifting the signal to omega 0. Okay. Now we'll discuss some problem. So we need to find the continuous time Fourier transform of the signal x of t is equal to e raised to j omega 0 t. So an exponential signal, we need to find a complex exponential signal, we need to find the Fourier transform of the signal. So in order to solve this particular question, we'll take one standard result, that is a Fourier transform of 1. Okay. Fourier transform of 1, we already calculated in the previous lecture. Fourier transform of 1 is equal to 2 pi into del of omega. If you know this particular result, we can easily find out the Fourier transform of x of t is equal to e raised to j omega 0 t. Because we know that the Fourier transform of 1 is 2 pi into del of omega. And you can write this particular term as e raised to j omega 0 t into 1. So if you multiply 1 with e raised to j omega 0 t, then you can apply this frequency shifting property in this particular problem. Because here x of t is equal to 1, then the final result will be the shifted version of the transform. So here the transform is 2 pi into del of omega. So if you multiply with the e raised to j omega 0 t, it becomes 2 pi into del of omega minus omega 0. So in frequency domain, we know that del of omega minus omega 0 means an impulse signal which is located at omega 0, and whose area is 2 pi. So 2 pi into del of omega minus omega 0. So this is the transform of the signal e raised to j omega 0 t. Now we can see another question, cos omega 0 t. And in order to solve this particular problem, again, we can use the frequency shifting concept. because we need to find the Fourier transform of cos omega 0 t. Okay. And we know that cos theta by using Euler's formula, it's e raised to j theta plus e raised to minus j theta by 2. So here also we can apply this particular concept. So we can write it becomes e raised to j omega 0 t plus e raised to minus j omega 0 t by 2. Okay. And by applying linearity property, we already discussed the linearity property of CTFT, continuous time Fourier transform. So we can individually calculate the Fourier transform. So we can split this equation like this. So 1 by 2 into Fourier transform of e raised to j omega 0 t plus 1 by 2 into Fourier transform of e raised to minus j omega 0 t. So by applying the linearity property, you can find the transform of the signal individually, and finally we can combine. Okay. So here we'll get two equations, two signals, e raised to j omega 0 t and e raised to minus j omega. So we already approached this kind of problem because e raised to j omega 0 t. So from the standard equation, the Fourier transform of 1, we can write 2 pi into del of omega. Now it is multiplied. The first signal is simply e raised to j omega 0 t into 1. And if you use this particular rule, uh, frequency shifting property, you can write the equation becomes 2 pi into del of omega minus omega 0. Similarly, the second term, uh, it's e raised to minus j omega 0 t. So if you consider the second problem, e raised to minus j omega 0 t into 1, you consider this way. We know the transform of 1, and if you multiply with the e raised to minus j omega 0 t, it becomes 2 pi into del of omega plus omega 0. So, and finally, you can find the Fourier transform uh, of cos omega 0 t. Okay, we already written the expression by using linearity property. So you can write it becomes 1 by 2 into the transform of e raised to j omega 0 t is 2 pi into del of omega minus omega 0, plus the next term is 1 by 2, 2 pi del of omega plus omega 0. And if you combine this, it becomes pi into del of omega minus omega 0 plus del of omega plus omega 0. So it's a very interesting result because we are actually finding the transform of a cosine waveform. And if you find the transform of a cosine waveform, so this is a sinusoidal waveform, or in other words, so this is a cosine waveform in time domain. So this is in time domain, and this is cos omega 0 t. And the transform of this particular signal in the frequency domain will be like this. It will be two impulse signal which is located at omega 0 and minus omega 0. See, you can see one signal exists at omega 0, another one at minus omega 0. So this is del of omega minus omega 0, and the area is pi. So here it is del of omega plus omega 0. Okay, this is the transform of the signal. The signal is x of t, here it is x of j omega. Okay. So this is a cosine signal, so it contains only one frequency component, omega. Okay. Similarly, you can approach the next problem, sine omega 0 t, and you can see by using Euler's formula, you can expand sine omega 0 t like this. So we can write the Fourier transform of sine omega 0 t can be written as the Fourier transform of e raised to j omega 0 t minus e raised to minus j omega 0 t by 2j. So we can apply the linearity property here. So you can split this particular expression. So you can write 1 by 2j Fourier transform of e raised to j omega 0 t minus 1 by 2j Fourier transform of e raised to minus j omega 0 t. So by applying the linearity property, you can split this particular expression, linearity property of CTFT that we already discussed. So we can find the transform individually. So the transform of e raised to j omega 0 t, you can find out if you know the Fourier transform of 1. So Fourier transform of 1 is 2 pi into del of omega, 2 pi into del of omega, and you can apply the frequency shifting property. That is, if you multiply the signal with e raised to j omega 0 t, it's simply the shifted version in this frequency domain. So it becomes omega minus omega 0. And next term, e raised to minus j omega 0 t into 1. So the continuous time Fourier transform of the signal is 2 pi into del of omega plus omega 0. Okay, now we can combine these two results. So the Fourier transform of sine omega 0 t is equal to 1 by 2j, and the Fourier transform of the first term is 2 pi del of omega minus omega 0. Okay. And the second term, if you again, this is 1 by 2j, if you take 1 by 2j common, it becomes minus del of omega plus omega 0. Again, you will get two impulse signals. One is located at omega 0 and another one is minus omega 0. So if you simplify this, it becomes pi by j, okay, del of omega minus omega 0 minus del of omega plus omega 0. Okay. So if you take the magnitude of the signal, again, you will get the two impulse signal, which is located at omega 0 and minus omega 0. Okay, 2 will cancel, it becomes pi by j. Okay, this is a Fourier transform of sine omega 0 t. Now we'll discuss another question. If you look at this particular question, it seems almost same the previous question, but there is a difference. It is actually cos omega 0 t into u of t. So when you consider this particular question, you can write the Fourier transform of x of t, that is simply cos omega 0 t into u of t. Then cos omega 0 t, you can write e raised to j omega t. So you can split this like this. Cos omega 0 t, you can write e raised to j omega 0 t plus e raised to minus j omega 0 t by 2 into u of t. So your equation becomes like this. And you should also look at this particular equation. There is already a result e raised to minus 80 into u of t. And the transform of the signal is 1 by a plus j omega. But here you cannot apply this particular property because it's a complex signal, e raised to j omega 0 t. You can apply this result only when the signal is a real signal, e raised to minus a t. Okay. When a is a real quantity, you can apply this particular property, but here you cannot apply this. So we need to use the transform of u of t here. We know the transform of u of t is 1 by j omega plus pi into del of omega. So we already explained the transform of u of t in another video. So by using this particular result, u of t, the transform of the step signal is 1 by j omega plus pi into del of omega. You can apply the frequency shifting property in this particular problem. So if you rewrite this particular equation, it becomes e raised to j omega 0 t into u of t, okay, by 2. So you can take this a common factor, then plus the Fourier transform of e raised to minus j omega 0 t into u of t. So the transform of u of t is written u of t. The transform of u of t, it's simply 1 by j omega plus pi into del of omega. This is the transform of step signal, continuous time Fourier transform. If you know this particular result, you can apply the frequency shifting property in this problem, because the given question is something like this: e raised to j omega 0 t into u of t. If you know the transform of u of t, you can find the transform of e raised to j omega 0 t into u of t. You can simply shift the signal. So 1 by j omega minus omega 0, and there is one more omega, so you can apply the shifting property in impulse signal also. So this is the transform of the signal e raised to j omega 0 t into u of t. Now we can take this next term, that is e raised to minus j omega 0 t into u of t. And if you apply the frequency shifting property here, you can apply, it becomes 1 by j omega plus omega 0 plus pi into del of omega plus omega 0. Okay. Now we can combine the result by applying the linearity property. In this particular problem, we are actually applying two property. One is the frequency shifting property and the linearity property. So when you do the problems in exam, so please mention all these properties. So now we can combine the result by applying linearity property. This is the frequency shifting property. Now we can combine the result by applying the linearity property. So the Fourier transform of the signal cos omega 0 t into u of t can be written as 1 by 2, okay, into 1 by j omega minus omega 0. Next term, it's 1 by j omega plus omega 0 plus pi into del of omega minus omega 0 plus pi into del of omega plus omega 0. So now we can simplify this particular equation. So when you simplify this particular equation, you will get 1 by 2. Okay. And if you take the LCM of the first two terms, it becomes j 2 omega divided by j omega the whole square plus omega 0 the whole square. Okay. And the next term, it's simply pi into del of omega minus omega 0 plus omega plus omega 0. Okay. So this is a simplified result. You can also multiply with 1 by 2 to simplify one more step. Okay. So this is the result of Fourier transform of cos omega 0 t into u of t. So make sure that whether the given question is simply cos omega 0 t or cos omega 0 t into u of t. If it is into u of t, you need to apply the result of u of t to solve the problem. That is step signal. The transform of step signal we need to use. In the previous case, it's simply a sinusoidal signal or a cosine signal. Okay, you can see that the result is different for two cases. Now we can apply the sine omega 0 t. Okay, when you apply the sine omega 0 t, again we can approach the same Fourier transform of sine omega 0 t into u of t. You can apply by expanding in Euler's formula. So you can write the sine omega 0 t like this: e raised to j omega 0 t minus e raised to minus j omega 0 t by 2j. Okay, into u of t. So again, we need to use the transform of u of t, and we can split. So it becomes 1 by 2j into Fourier transform of e raised to j omega 0 t into u of t. That's the first term, and minus Fourier transform of e raised to minus j omega 0 t into u of t. Okay, in the same way you can approach. So if you expand this expression, you will get e raised to j omega 0 t into u of t that we already got. The expression, it's simply 1 by j omega minus omega 0 plus pi into del of omega minus omega 0. For the second term, it's e raised to minus j omega 0 t into u of t. By applying the shifting property, you can write 1 by j omega plus omega 0 plus pi into del of omega plus omega 0. So here we are applying the frequency shifting property. In the first case, we are applying the linearity property. Okay, here we are applying the linearity property. Here it's a frequency shifting property. Now we can combine the result, and the Fourier transform of the signal sine omega 0 t into u of t is equal to 1 by 2j. Okay, 1 by 2j is a common term, and remaining term is 1 by j omega minus omega 0 plus pi into del of omega minus omega 0 minus 1 by j omega plus omega 0 minus pi into del of omega plus omega 0. Okay, because here it is minus, so we can apply that minus here. And if you simplify this, you can simplify this expression. It becomes 1 by 2j, and if you take the first two terms, it becomes 2j omega 0 divided by j omega the whole square plus omega 0 the whole square, plus you can take pi common, then it becomes del of omega minus omega 0 minus del of omega plus omega 0. Okay, so we got the final equation. You can also simplify by simply multiplying with this 1 by 2j. Okay, you can write one more step. So if you multiply with 1 by 2j, it becomes omega 0 by j omega whole square plus omega 0 whole square plus pi by 2j, okay, into del of omega minus omega 0 minus del of omega plus omega 0. Okay, now we can do one more question in the next lecture. Okay, so this problem we'll discuss in the next lecture.